want to do break? Maybe we can go about it.
Yeah. Hey, thanks everyone for coming back. It's always nice when after you give a talk and there's still people in the audience to see the next one. So thanks all for coming back. So we're going to change gears a little bit and talk about computations. So, like I mentioned, the original plan that me and Miguel outlined was to start with the math and then weave through 3 different kinds of applications and then talk about how to compute. So once you were sufficiently hyped up that Bordism was the thing you wanted to look at, we tell you how. But Miguel is currently feeling a little sick, and so that's why he wasn't here yesterday or today. And so we'll see if he, we're playing it by ear, but I figured I'd give my part of the computations talk today, and then we come back later to more of the applications. So yeah, so if you're feeling bored, well, I guess there's more Bordism, sorry about that. But I guess the key thing, so the point of this talk is, if you've seen the Bordism groups, you want to compute. So typically these would be things like, okay, so we're going to talk a lot about this, about the Bordism conjecture and anomalies, later this week. But so that would be, I think, for this audience, those would be the Bordism groups you're interested in. You're like, okay, I have this particular, heterotic string theory. I can check if it is an anomaly by computing this Bordism. Great. How do you do that? That's sort of the point of this talk. I'm going to show you, some of the field of computational techniques. So this isn't a classroom where I'm going to say, here, I will teach you exactly how to do this, but I'll show you what they look like, try and tell you which things are easier and harder, and crucially, where to go to learn them. One good answer, by the way, is I'm always happy to talk about this stuff. I think it's so cool that these things that I learned for their, for my own mathematical enjoyment are showing up in physics. And so I'd love to see more papers that use these techniques. And I'd be happy to talk to anyone about that. I think a key thesis is that these computations are tractable.
Could you please write a little bit bigger?
Yes, thank you.
No, yeah.
This?
Yeah.
Thank you. So, building on work that mathematicians have been doing since the 50s, the computations that show up in physics, especially in the physically relevant range, say dimensions 11 and below, 12 and below, we can do it. It's really possible. In some cases, it's easy. And in the hardest cases, it's still it's workable. And so, it's still pretty streamlined. There's still parts of the story that are that are still kind of an art rather than a science, but mostly it's, I'd say mostly it's, what's the word? There are a lot of computations where the path is less clear. Let's say that. So, okay. So for example, typically in mathematics, there's a question of, can we do this for all dimensions at once? And so when mathematicians will say something like, oh yeah, spin boards, and that's quite hard, they mean in every dimension, we don't know the full ring structure. That's literally actually still an open problem. But if you just want to know spin boards in dimensions 7 and below, say you have some question about a 5-dimensional quantum field theory, that was done by Milnor a long, long time ago, before 60s or earlier. So the things that are useful for physics are easier, different questions than the mathematicians are used to. And so this allows for some shortcuts. So
we have more here.
oh no, there's lots of chalk here. It's just that was a good one. Yeah, thanks though. So what am I going to do today? Let's. Yeah, why don't we just? Okay, yeah, why don't we do that? So maybe the steps to doing Bordism problem. The first thing you might want to do is probably determine, like, you want to, so given that this is a math question, it's important for us to precisely, to make sure we're answering the correct question. So the first thing you do is you determine the symmetry type. So what fields and what symmetries do you consider? So for example, let's say you want to know whether M theory has an anomaly. You could start by just saying psi is spin. M theory makes sense on spin. But M theory has this parity symmetry, right? So you can put it on pin plus manifolds. So if you don't care about parity symmetry, maybe you say, okay, this is just spin. If you do, maybe you say this is pin plus. Maybe you also want to take into account the C field. And then you need to do something like something fancier. And that's what Fried and Hopkins do with MC Bordism. But you say, what fields do I want to care about? Which ones do I not want to care about? What is the structure on spacetime that I get from those? For example, spin, pin plus, spin crosses E2 if I have a principal Z2 bundle. So this thing, on the scale from art to science, this is a science. So, I'm not saying it's like an algorithm that you can sort of ask a computer to do. But it's the kind of thing where after you do a few examples, you really get the hang of it. So then there's the question of, well, okay, well, psi Bordism is, I don't know. But maybe I can say that this is oriented Bordism of something, or spin Bordism of something. So as an example.
Sorry, I don't understand what.
Yeah.
So what is a bracket and something?
So I can take, shoot, right, I think I did not say this in the correct order, so let me back up. Let me think about this. So what I want to say is Bordism of a space X. So let me actually just define that over here. So one variant of Bordism I can consider is manifolds which have a map to some space X. And then I want the Bordism, when I say this bounds, I mean both as a psi manifold and the map to X extends across the board. So the tools that we have for computing are really good at saying if the symmetry type is simple, like SO or spin or O, but the space that I'm mapping to is more complicated. The tools are better at those kinds of things than at directly attacking a complicated symmetry type. So if you can re-express psi Bordism as oriented Bordism or spin Bordism of something, then your job will be easy. Yeah.
So if X is a classifying space, does it like feed back into the Xi? Does it change the Xi?
Yeah, so you could even think of this as, let's say I have, you can just think of this as B cross X, and then the map is only trivial or only non-trivial on the first factor. So in some sense, omega of psi of X is omega psi of X. Like I could include X in the symmetry type, or I could say Bordism of manifold
Any X, not necessarily a classifying space. Any X.
Yeah, X could be anything.
Okay.
Yeah, but it is often a classifying space. Yeah. Great. More questions? So just as an example, there's an isomorphism between pin minus Bordism and spin Bordism of the classifying space of Z2, so RP infinity. There's something sneaky going on here where I have to shift the dimension. And I have to take reduced spin Bordism, which means that what I do is that I quotient out by the spin Bordism of a point. So that's a, let's see. Yeah, I wouldn't worry too much about the precise details. The point is that the tools we have for computing pin minus Bordism, they're not as good at taking pin minus directly, but they're really good at saying spin. Spin Bordism I understand. And then of a space, BZ2. So the computations of pin minus Bordism that I know of, other than with one exception, they all go through this. So this is a simplification technique. And because of reasons of timing, I don't really have time to get into how this goes, but this is so this step is more of an art. But I will say that sometimes you don't need it. So for example, let's say you care about spin manifolds with an SU2 gauge field. Then you just have the spin Bordism of BSU2, and that's already in this form. So you don't need to worry about this. And they're also, in some classes of examples, you can just invoke a theorem. So just to reiterate, though this step is a little more of an art than a science, there's a lot of times when you don't have to worry about it, and there's a lot of other times when someone else worried about it for you. So for example, let's say you cared about spin times G, modulo like some common Z2 X. So this comes up in these like condensed matter examples where you have like a fermionic, like a group GF, that's the fermionic symmetries, but this includes Z2F as a sum. So these things, you can sort of like, someone has already taken care of this for those, and so you can just read that theorem, invoke it, and move on with your life.
So with this, you can do also spin C structure, I guess. No?
Yes, yes, exactly, yeah. So this is like a generalization of spin C. And indeed, there's a version of this theorem that spin C Bordism is the same thing as spin Bordism of BU1 shifted, and then there's the same reduced thing.
In the left-hand side, you're reading spin C.
Oops, let me write that there. Yes.
Okay.
Yeah,
But
thanks.
what's the reason of this shift? I mean, intuitively, how do I?
Do you know what a Smith homomorphism is?
Sorry?
Have you heard the word Smith homomorphism?
No.
Okay. So the reason for the shift is
It has to do with the fact that you have to take a bundle, no? I guess it's the size of the fiber. Or...
yes.
Okay.
Yeah. So it's the fact that the tautological bundle over this is a line bundle, and so that's the shift there.
Yeah.
The tautological bundle over this is rank 2,
Okay.
and that's the shift here.
Well, rank 2 real, you mean?
Yes.
Okay.
Yeah.
Okay. Okay.
But the dimension is also real.
Okay. Fine.
Yeah. Sorry. To me, all vector bundles are real, but we have some algebraic geometers here, so I should be careful.
But in the other case, you had a discrete bundle, no? It's Z2.
Yes.
How should I think of it as a real one dimension?
Well, so Z2 is the same thing as O1, right?
Yeah.
And so
But the fiber is 2 points. No?
I could take those 2 points and take the associated line bundle,
Okay.
right? So like U1 bundles are the same thing as complex line bundles, and O1 bundles are the same thing as real line bundles. So this thing has a tautological Z2 bundle, but it also has a tautological line bundle. So for those of you wondering whether you can do this with like SU2, and there is something, it's called spin H Bordism. There's a 3 here, or I guess it would be SO3, but yeah. So there is a third analog of this. So yes, spin C is a good example. The point is, in a lot of cases, these theorems already exist. Were there more questions? So the next step would be so once you've simplified it in this way, then you can run the spectral, or you can set up a spectral sequence. So there's two examples that show up a lot. One is called Atiyah-Hirzebruch. And another is called the Adams spectral sequence. The reputation that these have in the field is that the Atiyah-Hirzebruch spectral sequence is nice and friendly, the Adams spectral sequence is terrifying and scary. These can both be true and are also often wrong. In any case, they're both our friends, and I'll tell you about them, and I'll also tell you a little about what spectral sequences are. Not again, not in like the complete detail, because we only have an hour, but enough maybe to like get you started on actually reading more. So you pick which spectral sequence you want to use, you set it up, and this step, this is a science. So maybe this part is like, is a thing where you have to think creatively and try some stuff. But once you have that, this part you can kind of just do. Step 4, run the spectral sequence.
So by science, you mean that you can put the problem in a machine or almost?
So that's heuristically, yeah. So I don't think there is a program that is written that just says, here is this thing, here's the input, here's the spectral sequence input. But you can basically, so for example, for Atiyah-Hirzebruch, you need to look up the cohomology. And so, or you need the cohomology to determine the E2 page. And so you can just sort of look it up, figuring out wherever that's calculated, take that and then just put it into the spectral sequence. So once you know the cohomology, then a computer can tell you the input. For atoms, it's the same thing. You need something slightly stronger than that. But once you have that, you can ask a computer to, and in fact, that's what people often do is they just say, hey, computer, tell me this thing. And then the computer gives it to you, and then you can start on this step. So it's more like with a computer together, you may have to look up a reference for this, but once you have that, the computer can tell you. Yeah, hopefully that was a coherent way of saying it.
Maybe you need to have some information about higher differentials.
Oh yeah, that would be this step. This is just getting to the E2 page. Yeah, honestly, as far as I'm concerned, higher differentials are, well, they're hard, but that's okay.
Are you going to give an example?
Yes. So what we're going to do is, so once I talk about sort of the general perspective, I'm going to say, well, what is a spectral sequence a little bit? There's going to be an Atiyah-Hirzebruch example where we're going to find Witten's SU2 anomaly. And then there's going to be an Adams example where I'm going to talk about anomalies of n equals 160 supergravity theories. And like, you can look, you can learn something from a calculation about them. But the goal, the theorem is not the point. The point is more, what does this calculation look like? What parts of it are easy? What parts of it are hard? Yeah. Who has more questions? Okay. So running the spectral sequence, this is sometimes trivial. So in the Atiyah-Hirzebruch example that we're going to do with Witten's SU2 anomaly, it's trivial. Like you set out the spectral sequence, you look at it, and you realize that there's no more work to do. Sometimes realizing there's no more work to do is hard, but in this case, it's not so bad. Sometimes it's non-trivial, but not too bad. So for example, there's, pre-existing tricks come to your defense. So often if you're like, okay, I have this obstruction to like, I have a differential that I don't know, or I have an extension problem I don't know. And then you look and someone has solved a similar problem before. You can just take their thing and make it work. And this is especially true in low dimensions, which is good because physicists care about low dimensions, 12 and below. Otherwise, this is pretty hard. So to summarize, sometimes, you can sort of test a couple small things on it and say, oh, is this trivial? Does this follow from one of the tools in my toolbox? And if so, I'd call it science. But often enough, it's an art and a difficult one. So I guess my take on it is don't worry. In a lot of cases, it's perfectly tractable, but every once in a while it throws you for a loop. Then the last thing that you may want to do is find generators. So remember, these Bordism groups, we built them out of manifolds. And so if I got like Z plus Z2 for some Bordism group, I would like to say, okay, what manifold corresponds to 1, 0? That is some n-dimensional manifold with this whatever structure. Which one? Which structure? And then the Z2, which manifold? Which structure? So this is helpful because, for example, if we're computing some anomaly, we would like to be able to say, okay, I want to test whether it vanishes. So let's test on the generating manifolds. Oops.
What is your definition of anomaly in this case?
So Miguel's going to talk more about this later this week, but as far as I'm concerned, an anomaly is, so a quantum field theory is anomalous if it lives at the boundary of an invertible field theory in 1 dimension higher. So, so then the anomaly is that invertible field. And so, as I mentioned last talk, we can classify all the invertible field theories using Bordism. And so you might, and so you want to compute the partition function on, well, on everything. So you just check on the generators of the Bordism group. Because like the fact that the partition function is a Bordism invariant is telling you you only have to look at a few examples. And so you have to actually find, if the spectral sequence spits out this algebraic information, you have to find the geometric stuff that that represents it. So I'm not going to say much about this, other than the fact that this is an art. It can be difficult. And but maybe it's helpful to look at other papers solving similar problems. So this one really, this is hard. So as an example, there's this, so Miguel and I and Marcus Giorgio and Jonathan Heckman have this paper where we studied the anomaly of the duality symmetry in type 2B string theory. And so this part, there was a little bit to say here, like how does SL2Z mix with fermion parity? And it turns out they mix, and so you get one of these. But it was not trivial, but it wasn't so hard. This step was actually not so hard. This was a science. And then it took us a little while, maybe a month or two, to figure out, to finish the spectral sequence and run it. But this stuff took a long time. So coming up with generators in that case was harder than average. But like, it's sometimes you test on the examples that you know, and sometimes that works and you're done, and sometimes you just really have to stretch your brain thinking of new things. So if you don't need this, great, and there's like less stuff for you to do. So this is just a heuristic overview of what the problem looks like. The next thing I want to do, well, first I'm going to check the questions, and then I'm going to start getting a little more concrete. Like I'll talk about what a spectral sequence is, we'll talk about a Tier-Herzebruch, and then we'll see a computation. But first questions. Yes.
So once you know what the Bordism group is it easy to say what the Bordism class of a given manifold is?
Not yet. So once you have generators, it's a little. So typically, what you do is you compute Bordism invariants. So you find that you find a set of functionals on the Bordism group that collectively detect it. And so then you calculate those invariants on your manifold, and then you know exactly where it is. But that's about as hard as this. They're sort of dual problems. Yeah, great question. Yes.
Is there any way to compute generators from the spectral sequence, or they are completely unrelated problems?
Also a great question. So the answer is pieces of the spectral sequence sometimes tell you information. Like they'll say something like, so the atom spectral sequence will tell you if you're in the bottom row, it'll tell you, oh, you can detect a generator by this particular cohomology class. So integrate that cohomology class, and if it's non-zero, you found a generator. So it provides you partial information, and there's a few other ways to get to get a little more information, but it won't be a complete story. So it's this kind of weird thing where it's like, it feels like not mathematical. It's just like this very ad hoc hands-on thing. But maybe that's what makes it fun. I don't know. More questions? Yes.
I was puzzled because somehow you are now understanding the Bordism ring, but in the previous talk you talk about the Bordism category. And these are two completely different stuffs. In particular, typically for the Bordism category, you apply more theory.
Right. So this is all about Bordism groups. So like the part that's the pieces of the Bordism ring. And the reason is that the classification of invertible field theories, we started with the category, and then it's a theorem that if you want to classify them, you just need to use these groups. So honestly, for the rest of Miguel and I's talks, we're probably going to forget about the fact that there was a category. Forgetting about categories will make some people happy and other people less happy. I will not tell you which one of those two I am. Did that answer your question?
Yeah,
Great. Okay, cool. Who has more questions?
I have a request.
All right.
Can we go for the details?
Yeah. So what I'm going to do is I'm going to tell you roughly what spectral sequences are, and then we will have a detailed example. Yeah, sorry. So spectral sequences have a reputation in mathematics. Ravi Vakil writes in his algebraic geometry book that, why are they called spectral? Most things in mathematics, if they're called spectral, they're related to the spectrum instead of eigenvalues, right? And this is, indirectly related to the spectrum in quantum mechanics and in, actually colors coming from like the quantum mechanics of an atom. But in homotopy theory, when someone says spectral, it's unrelated. So Vakil thinks, spectral sequences, it's because they're scary, like specters or ghosts. He then says, I have heard nobody disagree with this interpretation because I just made it up. So I think this is a little bit unfair. So spectral sequences, it's a big thing with a lot of moving parts, but it's a lot like cohomology. When you first learn cohomology, you're like, wow, this is complicated. There's so many things. How do I compute some examples? But eventually you get used to the way that it works. You get the feel of what happens when you turn the crank, which parts might jam. And spectral sequences are just like that. So spectral sequences are so like cohomology, there's a bunch of moving parts. And, the construction is involved. Let's just forget about that. So when I say it's involved, I want to clarify. There's some things that people are going to talk about here, like Gromov-Whitman variants, which are involved because you have to do a bunch of hard, deep math. This is involved because you have to do a bunch of homological algebras. It's shallow and flat. You have to do a large number of little things. But still, when you read these books on spectral sequences, they're like, all right, let's start with an exact couple, and now do this computation, and now chase this thing around, and now apply the snake lemma 3 times, and now this, and soon you're falling asleep on the train. And I'm going to tell you, you're reading a book about, like, I don't know, the next chapter in your favorite comic book character, and it's deeply, deeply boring. So you skip to the good stuff, right? And I'm telling you, do the same thing here. You should really, so I think the best way to understand this, like most computational tools in mathematics, is use it. And then once you know that you need it or want to keep doing more of it, then you can read about why it works. So skip the proofs and read and then come back to them, which I guess because this is mostly a physics audience, people already know that. But it's useful to think about this as a black box. So these things are two-dimensional generalizations of chain complexes. And then maybe, homology. So as a reference, I don't know, it's hard to know. Honestly, the best way to do this is to just get one's hands on some examples. I personally like Loring Bott and Raoul Bott and Loring too have this book called Differential Forms in Algebraic Topology. It's a wonderful, lovely book, and in part 3 they do some spectral sequences. And what I don't mean is read through from beginning to end of this part. What I mean is read their spectral sequences, maybe read elsewhere, and use their examples. Like they compute the cohomology of loops on S4 or something, And working through that will help you understand it better. Just like doing the exam. You know, we tell our students, what's the word? Flipped classroom. And if I could, I would absolutely run this lecture that way with like examples and problem sets and everyone else at the chalkboard. Because that is the best way to learn this stuff. So do the exercises. So the general setup. So you begin with the second page. It's called the E2 page. Why are we starting with the second page? That has something to do with this black box that I told you to not worry about. So this is a bi-graded abelian group. Sometimes people do this with like vector spaces instead, but that's fine. And it's typically drawn like this. So here's P, here's Q, the two gradings. And they'll write, so maybe like here's Z. If something is 0, you don't write it. I'm just writing a heuristic. So this is just an example of like what this might look like. So we have a bi-graded abelian group. And so here are the elements in different places. So for example, E2, 2, 0 is Z. So we're on the E2 page. P is 2, Q is 0. Actually, wait, let me write this the other way. Don't worry about why I did that. Just I think it's more consistent with the literature. So what we're going to do, you should think of this as like a two-dimensional chain complex. So if you remember, chain complexes had differentials. So there are differentials between the various abelian groups. So here I need to choose what I'm doing, like homological or cohomological type. So there's different grading conventions. So we're going to do the homological type. So we're going to do the homological grading convention because Bordism is a homology. And so the differential is a map to PQ. So the differential on the E2 page, it's going to be a Knight's move upward. So like this. So it's going to go from PQ to P minus 2, Q plus 1. So it turns out that D2 squared is 0. So we've made these sort of diagonal chain complexes. So whatever a spectral sequence is, we start out with this data. And we sort of have a bunch of chain complexes. So
Do you mind reminding the definition of P2PQ?
Oh, what? Oh, wait, did you say P or?
Yeah, the
So-
definition of P2PQ.
So P and Q are the two different Z2 or Z gradings.
Yeah, I mean, you start with a bicomplex. How
Yes.
do you define P2PQ?
Oh, I'm so sorry. So I was planning on taking that part as a black box, that someone hands you the E2 page and says compute. So, and then later you can go back and say, okay, well, there's a bicomplex. How do I get that page? Yeah, sorry. I would have to review how that goes actually before I presented it.
Oh, it's easy. First you take differential upstairs, then you compute for homology, then.
Right, but then where does this come from?
less,
And that's a diagram chase.
and yes.
Yeah, that's the thing that I didn't want to get into.
Yeah, but this is just a comment. For me, the most scary part of the spectral sequences is that the blue arrows are completely implicit. You have no knowledge about that.
Yes, yeah, no, this is a good point, that the differentials. So our goal is to figure out what these blue arrows are. Maybe I should write that. So once we have that, then we can turn the page into spectral sequence. But like you mentioned, it's not always clear what the differentials are. So a priori, there's no obvious definition. In some spectral sequences, there's an answer, and then you use that. But in general, so once you do that, you can turn the page. So, you know, maybe someday I'll write a book on this, and I can only hope that it's going to be a page turner. So then you get the E3 page is the homology of the E2 page with respect to the differential. Right, so you would say, okay, so for example, let's suppose that this differential is an isomorphism and all of the rest are 0. So then we would say, okay, 0, 1, 2, 3, this is P, this is Q. So so this Z stays the same, but now, so these things, we have an isomorphism. And so you want to take, for example, at this point, you take kernel mod the image. So the image is coming from over here, which is 0. So the kernel is 0, mod the image is 0. So we're going to get a 0 here. And here, the kernel is everything, because this goes to 0. And the image is everything. So we're going to get 0 again. So this thing is now 0, and this thing is now 0. And everything else didn't change. Okay. So we've now simplified this. So how do you actually tell that? That depends on the spectral sequence. But the point is we've now turned the page and we found the E3 page. And on the E3 page, we have a differential. And now, instead of being a Knight's move, it's a generalized Knight's move. So we take P minus 3, Q plus 2. So it would look something like this. So why do you get a differential that, why does the differential change? We started out with something that looks like this, and then it got longer. And this is one of these homological algebra things where someone says, just chase the arrows, it'll be okay, and then don't, one of those diagram chases. And so, I'd encourage you to just take this on faith for now, and then later go back and read it in, for example, Ravi Vakil's book in I think 1.7 or 1.6. But in the meantime, but the point is we now have another differential, probably harder than D2. So once you know D3, you can turn the page again. Oops. So once you know all the D3 differentials, you take the homology with respect to those and you get the E4 page. And you have D4. And once you determine those, you can turn the page and get the E5 page, and so on. Now, where does this stop? So one crucial thing that I did here is you'll notice that outside the first quadrant, this is 0. So if we're in a first quadrant spectral sequence, like we will be in all instances today, then what you notice is for any particular point, at some point, all differentials are going to be below this and then out there. After long enough, all differentials to this dot vanish. So to or from vanish. So in some sense, the spectral sequence converges in the following sense. There's stuff happening here, but as we keep turning the page, it starts stabilizing in this direction. So the spectral sequence may have infinitely many pages, but for any particular thing you care about, you're done after a short time. And this is especially nice because, in mathematical physics, we typically don't care about all of the stuff over there. Just like, say, the first one. And so the thing it converges to is called the E infinity page.
D3, D4, and so on do not come from the previous differential, right? They come from the bicomplex.
Yes. Yeah. So it's this. Yeah, I'm in particular not telling you how we got these differentials, but because I want to treat that as a black box for now. But yeah, the process that constructs the spectral sequence gives you all these differentials. Yeah. Thank you for mentioning that.
By the way, so in the end, what are we trying to compute?
So that depends on the spectral sequence in question. So I'll give you two examples and then say what the E2 page is, what the E infinity page is approximately. But typically what happens is the E2 page is some naive approximation of the thing we actually want. The differentials are telling you like the error terms in that approximation. And then the E infinity page is what we actually want. Yeah. So what we converge to is called E infinity page. By the way, does E stand for something? Does anyone actually know? I know different in some. I think I've seen like French papers which use H instead of E, which makes me wonder. And so you're again left with some bigrated things. So let's say we had Z. And we killed this and this. And let's say that D3 was an isomorphism, or sorry. So we killed this and this. And let's just say that everything else stayed the same. So at some point you're saying, okay, so for example, this thing is done, but this Z, a D4 is going to be either all the way down here or all the way over here. So as soon as you know that this is not hit by anything on the E3 page, it lives all the way to every other page. And so it exists on the E infinity page. And so in examples, the direct sum of EPQ is the associated graded of some filtration on the object you want. This is related to someone's question just now. So I'll say that in the end, we're computing something. And I'll tell you two examples soon of like things we might want to compute. And the E infinity page, it's the answer almost. So let's say we're computing like Bordism groups or something. This would be omega 0. This would be like, what's the color I use? So this would be omega 0. This would be omega 1. This would be omega 2. This would be omega 3. And then the sum of these would be omega 4. So it could be Z plus Z2 squared. But it could also be, so this is the associated graded of some filtration. So we could also combine these in a non-trivial extension. Like we might get Z4. And sometimes there are other options. I think in this case, this is, I don't remember, so let me know.
And what would be the second page?
What?
What would be the second page?
For Bordism? I'll say that in just a sec. It's the homology of the space with coefficients of the Born group point, but I'll write that down in a minute. Just the point now is the algebraic structure is we have the answer, except a Z4 might split into a couple of Z2s, for example, or a Z6, sorry, a Z9 into two Z3s, or a Z9 and a 0. So there's sort of the two questions of how do we determine the differentials, which is not always clear, and how do we determine whether we have a non-zero extension between things on the same line? And these two things are what make spectral sequences hard. So what I'll show you next, well, first there will be questions, and then I'll show you two spectral sequences to sort of make it concrete, like what we start with and what we end with. So first, who has questions?
So why would there a product? I mean, instead of a sum in the C2? I mean, like you had C plus.
Oh, this
mod
thing.
2 squared. Yeah. I mean, why not C mod 2 sum mods?
Why? Oh,
Why are you going to? Yeah.
let me write this. Okay, because I did the notation in a confusing way. This is what I meant. Sorry.
Oh, okay.
Yes. Yeah. Thanks for clarifying. More questions? Yes.
Yeah, in complex geometry, the way you use this spectral sequence, you want to calculate the Dolbeault cohomology, and then you relate that this fits into a bicomplex. But in the end, the goal is to calculate Dolbeault cohomology. Is there something similar here, or you're using this for a completely different? Or you start with a complex, and then you promote it to a bicomplex, and then you use all this to. I don't.
So
get it.
usually, I'm trying to think. Usually, we start from like a slightly different perspective. So, okay. So I mentioned that these are like two-dimensional versions of chain complexes, right? And so you're literally starting with a bicomplex. So sometimes I think what I want to do is I want to start with something slightly different, where I have like a chain complex and a filtration that are interacting in weird ways. So for example, maybe I have a, I want to compute generalized homology, say Bordism or something, and I have the CW filtration. And well, how do they interact? I don't know. And so out of that comes not necessarily a bicomplex, but a, I think it's like an exact couple. And then from that, you can do the same thing that you mentioned, like get out all differentials and whatever, algebraic in principle. Yeah, the bicomplex perspective to me, honestly, is a little clearer, like as in I understand it better, but I think it doesn't, I don't know if it always applies.
So would you say it's something like this that, okay, you want to compute a cohomology of some total space of some, I mean, cohomology of some bundle, and you think of that as a total space of a fiber bundle, and you know the cohomology of the fibers, you know the cohomology of the base, and you want to combine them.
Good. Yes, that is what I was going to say. So that would be, yeah. That's a good example, and I'm glad you brought it up because I'll say it next. But first, are there more questions? Okay, so we need some examples. So the first example is the Serre spectral sequence. Let's say I have a fiber bundle. F to E to B, and I want B to be simply connected. You can do it in a more general setting, but it's a little bit of a headache. So the goal is to compute the cohomology of it was Z coordinates. This seems hard, but you know what seems like a reasonable approximation? What if this were like kind of trivial? Or like, what if it were, what if instead I put CW structures on this and filtered the cohomology of the total space by the CW filtration downstairs on B. So we approximate with the cohomology of B with coefficients in the cohomology of F. And so what ends up happening is you get a spectral sequence whose E2K is the Pth cohomology of B with coefficients of the Qth cohomology of F. And we write this double arrow to mean the following. So this means, so this says that it converges to the cohomology of E, which means the thing you want. So sorry, let me try saying that again. So when I say this converges to the cohomology of E, that means that the E infinity page is the associated gradient of this. So in other words, there are these extension questions which are kind of annoying, but if you don't worry about them, for example, if you're working with vector spaces like you mentioned, then the E infinity page, you just sort of sum up everything on the diagonal and you've got the cohomology. So we started with our approximation, and the differentials are telling us here's the ways in which your approximation is not quite right. And then you have and then once you have all of them and you resolve the extension questions, you've got the cohomology.
So, sorry, do you have to put like homology instead of cohomology?
Oh, you're worried about the fact that the lower versus upper indices?
Yeah.
Yes, you're absolutely right. So if you wanted to do this, you would have to use cohomological grading, which means you'd reverse the directions of the differentials, but otherwise you're exactly right. Thank you.
Like I was asking if this spectral sequence is right with homology instead of cohomology.
Oh, yes, it is. Yeah, you get the same thing. I like the cohomology one better, but that's personal preference. But you have exactly the same thing for homology.
So this EPQ should be reversed.
Yes. Oops. Yeah, that's exactly right. There's a reason that in topology people are sticklers for these kinds of upper and lower indexing conventions because they really make a lot of this intuition much cleaner. So thank you for reminding me. Were there more questions? So we have just enough time to do the SU2 anomaly example. But first I should tell you which spectral sequence it is.
Sorry, in this case, do you also have to take some non-zero extension when you sum, or?
Yes. Yeah. In general, I guess I say that I would assume there's an extension problem unless there's some reason to believe otherwise. And so in this case, there can be.
I mean, it depends on E, I guess.
Yeah, absolutely.
I'm sorry, the filtration of the associated gradient of the cohomology of E comes from the cell structure of E, assuming it is a CW complex, or how do you do?
I think it comes from choosing compatible CW structures on E's that fit together into the CW structure there. Yeah. Great. More questions? So another spectral sequence is the Atiyah-Herzberg spectral sequence. So Atiyah and Herzberg introduced this spectral sequence. They remarked that they weren't the first people to know of it, but they were the first people to write it down. And this paper has it's like 10 pages and also introduces K theory and generalized cohomology. And it's like, really incredible. So we take a space X, and the E2 page is the it's the homology of X with coefficients in just Bordism, just the Bordism group, and it converges to the psi Bordism of X. So the idea, Bordism is like homology. And so we'd like to approximate it by actually homology. So in a nice world, Bordism would be perfectly easy to compute, and we would just say take the Bordism groups of a point, so there's no data of a map, and just take the homology of X valued in that. That sounds nice, but that's not actually the Bordism groups of X, and the differentials are the correction terms. So now I think this is the example, is the thing that a lot of you have been waiting for. So I'm sorry for the delay. So let's say you have a fermionic quantum field theory, and you want to study invertible field theories with this symmetry type. So for fermionic theories with an SU2 gauge. So these tell you so the invertible field theories for this symmetry type tell you, so they tell you anomalies for things in one dimension local. So if we can compute the fifth one of this tells us about a potential anomaly for 4-dimensional SU2 gauge. So that seems like a thing that would be nice to know. So Witten said there was one of these and it was associated to some homotopy group of I think SU2, but we're gonna get it from Bordism. So as Miguel's gonna mention, I think tomorrow, there's this close relationship between Bordism and anomalies. So we'll come back to that, but the cohomology of ESU2, or sorry, let's start with spin Bordism. So there's Z, Z2, Z2, 0, Z, 0, 0, 0 in dimensions 0, 1, 2, 3, 4, 5, 6, 7. Then after that, it does some more stuff. If you look at this and see Bott periodicity, that's part of the story, but not all of it. But the point is, spin Bordism. It starts with Z, Z2, Z2, 0. So we need to know the homology of BSU2 with Z coefficients and the homology of BSU2 with Z2 coefficients. So with Z coefficients, it's Z in dimension 0 mod 4 and 0 otherwise. So this, the cohomology ring is generated by sort of the first quaternionic quadrigon class, or maybe C1 squared, or sorry, C2. And then it's polynomials in that, and then the universal coefficient theorem gives you the homology. And with Z2, we apply the universal coefficient theorem again. We get a Z2 and 0 mod 4 and 0 otherwise. So now we can write down the spectral sequence. So here we have omega 0 spin Z, right? So here's Q, here's P. And so along this direction, we have the homology groups of BSU2 with coefficients in omega 0, which is Z. So we get a Z here, we get a Z here, we get a Z in degree 8, and everywhere else it's 0. Up next, we have omega 1 spin Z2. So we have a Z2 here, we have a Z2 here. So now we have Z2 again, so we get the same thing. In dimension 3, there's nothing. In dimension 4, there's Z. And then after that, there's a bunch of zeros. And there's going to be more stuff out this way and out this way. But as physicists, we don't care about this in like arbitrary degrees, just up to, say dimension 5. So this is the E2 page. Okay, I'm just going to work through this example and then take questions at the end. Sorry for going slightly over time. So we need to find the differentials. So the differentials, there's going to be a, so the D2s, for example, they're going to be night moves. So if you look, there's not enough room for there to be night moves, right? Like they're all going to, the things are too far apart. So D2 is always 0. Now you could look at D3. And again, in D3, there's also no room for anything to be interesting.
Sorry, so you automatically say that this is also the third page.
Exactly,
Okay.
yes. Sorry, so the homology with respect to a bunch of zeros doesn't change. So the E2 page is the E3 page. Thank you for making that explicit. I should have said that. But then on the E3 page, well, there's still not, this thing still goes here. This thing, it looks like it could be non-zero, but I have a torsion group mapping to a free one. So this is also 0. Maybe there's some others that might happen. But this thing is not, this thing is not affected by a differential on the E3 page. And on D3 equals 0 in total degree 5. And now looking at degree 5, D4 leaves. So what we conclude is that if you look at this, so the E infinity page, the total degree 5 is 0, 4, 1, 0, 3, 2, 0, 0, Z2, 0. So we take the direct sum of all of these, and that's an associated gradient. But the only way to get Z2 out of this is to include omega 5 spin of BSU2 E mod 2. And the reason is that we had a Z2 on the E2 page, and then we didn't need to know anything about the differentials. They all vanished automatically without having to think. So this is like, there are two kinds of spectral sequences. The algebraic geometers do things like this. They hope and pray that the differentials just go away and you don't have to think about them. Then there are the homotopy theorists, and you read these papers like, oh yeah. So they like put their knives between their teeth and climb into the jungle, and they'll say things like, okay, we resolve this D61 on the 61 page, and then after that, the spectral sequence collapses. And these papers terrify me. But nonetheless, someone can do it. So here we got to not have to worry about differentials. It's all, algebraic geometry is a nice place to be. And so we learned that this Borsen group is Z mod 2. So this corresponds to Witten's SU2 and all. The fact that this is non-zero means there's a potential for a non-zero anomaly for SU2 gauge theories in dimension 4, and that is exactly Witten's anomaly. So I'm already over time, so sorry about that. I'm going to stop here, and please let me know if you have any questions.
What is the generator here?
Shoot, that's a good question. I don't know that off the top of my head. It's going to be detected by some kind of theta invariance. So. Yeah. Okay, I can think about that. It's going to be a non-bounding circle times some form manifold, which has non-zero SU2 flux. Flux charge. I'm not sure if that's the right word, but it's going to be non-bounding spin circle and then something which has a useful SU2 bundle.
The mapping torus, no? I guess.
What?
The thing that is done in the paper of this mapping torus.
Yes, that should work. Yeah.
What is the intuition for this Satyajit bicomplex?
So my intuition is like I have a generalized homology theory. I'd like to pretend that it's ordinary homology.
Okay, so Miguel has answered in the chat, and he said that the generator is S1 times S4 with one SU2 instant on the S4.
Ah, perfect. Yes, that's right. Sorry. No. There's a reason that this makes sense. I thought it was going to be something times an S1. So the generator. Thank you, Miguel, for saving me. Is S1 non-bounding times S4, and we need a principal. So, and then we have a 1 unit SU2 flux. Here. So this is a standard way to refer to these things in physics. In mathematics, you want to say, I want a principal SU2 bundle on S4. So these are classified by a homotopy group, pi4 of BSU2, right? Because they're mapped from S4 to BSU2. And so this thing is isomorphic to Z, and we're taking the one corresponding to the generator. So I think a way to specify that bundle is the Hopf federation. So S7 is the unit sphere inside 2 copies of the quaternions, and then that has a projection onto quaternionic projective space, which is S4, and this is an SU2. So that's this bundle. And then we take that, we take the product with a non-bounding circle, and that's our generator right here.
Sorry, what is a non-bounded circle?
So, So the question is, do the words periodic and anti-periodic circle, or like Ramon and Hugo Schwartz, are these words that make you happy? I don't, like, people say some of this in so many different things. You may have heard of it with different wording. Okay, so there are 2 spin structures on the circle. One is bounding. is induced from S1 is the boundary of B2. But then there's one more. Which you can sort of get by taking the spin structure on the interval and then identifying the ends. And so this generates the first spin Borders effect. So when I say the non-bounding spin circle, I mean this one. Because otherwise you could say, oh, well, this is the disk times S4 with its flux as it bounds this, and that would be bad. But the other spin structure on the circle does not bound the disk, which is kind of weird.
So it's just a choice of a generator of the second cohomology in Z2 coefficient.
No, it's a choice of, I mean, it's a choice of spinor bundle, and there's two different ones that one of which extends to the disk and one of which doesn't.
Is not the same that Raul said?
I don't think so. Wait, so okay, look. Why would you say it's a choice of second cohomology?
Doesn't those classify spin structures?
Yes, so second cohomology, W2 tells you whether there is a spin structure or not. It doesn't tell you, like, it doesn't parameterize the different spin structures. Oh. Yeah, that's kind of a subtle point. The number of spin structures is the same thing as H1 with Z2 coefficients, but to actually pick a spin structure, you have to do a little bit more. Like you actually have to, you've got to find the spins. And so so honestly, there's a nice description of these in terms of double covers, but I messed that up once in front of a bunch of people, so I'm not going to try it again. It's counterintuitive, but you ask, okay, well, what is the spin one bundle of spin frames? And there's two choices given by the trivial bundle or the Mobius bundle, and they correspond to the two choices here. Yeah. Yes.
So coming back to Mario's question,
Yeah.
can we have some more intuition of why this spectral sequence computes this Borders into group?
Yeah.
And in particular, so you never mentioned the first differential, right?
Right.
So what would be the first differential here? So can I think of the first differential as the operation in the ring H star BSU2Z?
Oh, you mean like you start, so in the E1 page would be some sort of like chain complexes.
Yes.
And you take the different, yes, okay. So here's what's going on.
But what is this chain complex of the first page?
Great. So let's take the CW filtration on X, right? So we made this into a CW structure. So I got X by gluing a bunch of disks.
Yeah, but I don't really know what is a CW.
So are you happy with the triangulation? Like I turn X into a bunch of triangles and tetrahedron?
Yes.
Yeah. So what this means is I can sort of inductively build X by starting with one point, and then I glue on an edge and another point, then I glue on and then I fill in a triangle. So at every stage, I'm gluing in a disk. So if I take X at stage n, relative to X at stage n minus 1, this is a sphere. Right? Because I have like a new disk that I've glued in, and then I take everything else. I make it a point, and so now I have this disk plus a point, and that's a sphere. So now we're asking, okay, so we're sort of saying, okay, I want to consider only the piece, like each step of this along the way, the relative Bordesian groups. So the Bordesian groups of this quotient. So the Bordesian groups of a sphere. So that's going to be the same thing as the homotopy groups of of this Tom space that gives you Bordesian. And so that's going to end up, so generalized homology groups of a sphere are the same thing as the generalized homology groups of a point with a shift in degree. I think you can get that out of the suspension isomorphism. But the upshot is the E1 page is going to look like chains on, oh, what's the right way to say it? Oh, I may have done this wrong.
Chains of X with coefficients in the generalized cohomology of a point.
Yes. So the problem is, I think I went about this in the wrong direction because I said, let's chop up X when we should be chopping up this thing. And you can do something, right? Because then it looks like we already, like this should be chopping up the board. Okay.
Then it's horizontal is X and Y. So can one think of this as the search spectral sequence of some vibration?
No. However, there is a spectral sequence which combines both of these, called Serre-T algebra, where you have a vibration and a generalized homology theory. But I don't think it's possible to cook it, like to turn this into produce a vibration out of this. It's a very great question. It's just not correct.
Can you see it as a spectral sequence of composing two factors?
Oh, you mean Grothendieck?
Yeah.
Oh, probably. Okay. So though I do not know how to do it, I know it's possible. So there's this, there's a grad student at UT Austin named Rob Grigorek, who has on his website this set of notes called the Grothendieck spectral sequence in higher algebra. So there are these really nice lecture notes which just say, how can I get every spectral sequence anyone has ever heard of as a special case of the one that you're talking about? So in this case, yes. I mean, one of your functors is going to be Bordism and the other is going to be homology. And then
One is
it's going to be, you're going to get them from Bordism and from homology, defined on a suitable category. So yeah, you can do that. It's going to look a little weird because we're in topology rather than geometry, but it works. So coming back to your question, if you decompose the Bordism spectrum instead of X, then you're going to get the E1 page. So you'll be able to get something where you can decompose this into a bunch of pieces of ordinary homology. And then the E1 page is going to be chains on sort of the pieces. So you're taking what's called the Postnikov filtration here rather than the CW filtration here. So the fact that this gives you the same spectral sequence as a theorem of Maunder, but now you're taking
Pieces of what?
Yeah.
oh, pieces of the Thom spectrum, MT stuff. So maybe I should just write this. So it's pieces of the homotopy theory object that gives you Bordism. And so then when you're computing the generalized homology of that, the pieces are ordinary homology theories. So you're getting ordinary chains on X with some differential. And then when you take the E2 page, that's the usual differential on the chain complex, and you get the homology with coefficients in this coefficient ring. This was probably not a clear explanation, so if you want to talk about it more, I'd be happy to. But it comes from chopping this into ordinary homology. Is I think the succinct answer.
Yeah, this is also just a comment. I mean, maybe it's fair to say that there is a whole technology to create spectral sequences. Actually, there is a whole bunch of algebraic stuff in which you say, okay, I have a double complex with these properties, so I have a filtered object with these properties, and then I get a spectral sequence. And this Atiyah-Hizelbrugg spectral sequences appears like that.
Yeah, but the point is, what is the double complex you start with? And because this has the whole intuition, right?
But I don't think it comes. Does it come from a double complex? I don't know.
I don't
know.
This is what
No,
wasn't clear to me.
Right. That's like I mean I think you can get it from a filtered complex, but that's more general. Okay.
It's rather like a composition of functors. First, you take a wedge with spectrum and then take motor.
Right. But I mean, does every Grothendieck spectral sequence come from like? Can you get it from a double complex? Okay. Yeah. Well, then.
Well, this is something
Okay, I think
standard way.
at this point of confusion, maybe we can call it a lecture and head for lunch. Is that okay? So let's thank everyone again. Thank you.